Okay, so as Dan mentioned, this is a quick talk about the Metronome GC policy in OpenJ9. I'll have probably slides for 15-20 minutes, so I'll skip over some of them, so that later at some point people can read more thoroughly. First, let me just start with GC policies that we have available in OpenJ9. I'm not going to elaborate on them. I'm just going to say that GenCon is our default GC policy. It's kind of a good compromise between throughput and low pauses. And I'll be comparing at some point the Metronome with GenCon. So Metronome is specific for very low pause times, and if you really want to control, if you want to have a more stringent control over the pauses, then this is the most preferred GC policy. There are some other ones like opt-average pause. You can also control pauses, but Metronome is the most strict one. On a high level, what you can see is that there are GC cycles occasionally that are scheduled, and they run for some time, something like 10% of the time they're active. Depends really on application, heap sizing. They appear from a high level, they're concurrent with the application, but as a cycle. But if you zoom in into one of these cycles, you will actually see that there are stop-the-roll increments that when GC runs, and they interleave with applications. So either GC runs or application runs exclusively. They just appear from high level that they are concurrent. So these pauses that are by default 3 milliseconds long, and we have a strict control when they run. So scheduling of these increments is strict. And you'll see a little bit more of details, but the point here is to kind of guarantee the GC overhead, so we don't have too frequent or too long of these increments. So basically, we kind of guarantee the throughput of an application is not going to be compromised over some limit. There's some scheduling of this GC things that are manual or static. Like, for example, the start of a GC cycle is static. It will trigger when heap is 50% full. So you have to do a little bit of experimentation at the beginning and tuning when exactly, if this is a good default point. If you set it too high or too low, you may end up with a waste of memory. Or you can actually have a GC not complete incremental session, and then it will complete in synchronous GC with one last increment that is longer than 3 milliseconds. Anyway, if you tune it and set it up properly, everything should be incremental and with these low pauses. Scheduling of the increments themselves are very strict. So in such a way that in any 60 millisecond window in an active GC cycle, we guarantee to have at most certain number of increments. By default, this is 6. So basically, we guarantee it's going to be at most 30% of GC overhead in any 60 millisecond window. All these parameters like duration of an increment or the window size, the throughput guarantee 70%, or all these things are configurable through command line options. So you can tune, and reduce the GC overhead, for example, to 20%, or guarantee the throughput to 80%. But that will cost heap footprint. You have to provide larger heap. A little bit of a technicality about an underlying technology. This is a simple mark and sweep collector. Marking is concurrent. It's based on a snapshot at the beginning period as opposed to incremental update. I don't have time here to go into details how it works. This is well-known style of a collector. You can find it external literature, but The known facts, I'll just remind you that this is a preferred collector if you want a better pose control, because there is no like card cleaning phase, for example, that incremental update has it, but it also has comes with the cost that write barrier of the snapshot at the beginning is a little bit more expensive, and there's more floating garbage because all new allocated objects are kept alive. All these during the GC active cycle. Another interesting thing is how the heap is organized. It's actually region-based heap. And the most interesting and most used one is regions for small objects. So all objects are grouped in size classes. So regions all have all objects with approximately similar size in the same size class. There are 15 size classes, really the logarithmic scale from 16 bytes to 2 kilobytes. The next one type of a region is a arraylet type region. So basically you'll see a little bit more details on the next slide, but all arrays, any array that are larger than 2 kilobytes will be discontiguous. We separate or like split them into arraylets, and then we can put them in the special regions. There is a third type, large object, but it's really, really infrequent or possibly never happens, really. Those are scalar objects larger than 2 kilobytes. Motivation for this organization of the heap is dual. First, we control better, we have better control of fragmentation, because this is just a mark sweep collector. We don't move objects, there are no compactions, but it's also easy to control sweep in incremental / concurrent fashion, because you can, for example, sweep one region while application thread is allocating from another region. Arraylets, as I mentioned, discontiguous organization, representation. Array that are less than 2 kilobytes will be just treated as a small object, but if they're larger than 2 kilobytes, they will split. And then what we do here is we introduce array of these leaves at the beginning close to the object header. So there's basically, if you want to access, if a thread wants to access an item in an array, there's going to be a level of indirection. You have to first define the leaf it belongs to, and then index the leaf themselves. And finally, what are the performance expectations, or what are use cases for this GC policy? So it's recommended to use if you really want to, if you're really worried about the worst case post times, or if you really want to look into response time distribution. It should normally improve the 4.9 or 5.9 percentiles, while because of the throughput penalties, it will compromise the lower percentiles. Rough expectations is maybe the throughput will be around 30% lower than the GenCon's GC policy throughput, but it will highly depend on the really application behavior, because this is non-generational collector, very generational workloads will probably suffer a little bit more, but non-generational workloads will maybe suffer less. An example of non-generational workload is, for example, transactions that preserve a session, for example, call, that have a state that lives for a long period of time. So the death rate of the objects is not that high. Tuning is possible, so you can, for example, increase the region size, relate leaf, various parameters about scheduling, so you can decrease this gap a little bit even more, less. And again, there are ideas we can improve this, but you're welcome. Feedback is welcome, so we know what to focus really on. That's it, so if there are questions.
Thanks so much for giving the talk, Alex. Can you mention again, the kinds of workloads you would typically want to use Metronome for?
Yeah. Okay. So I'll repeat just the two bullets here. So like very generational workloads, with a high allocation rate and very low survival rate is probably not that good, because with the very large nursery and and infrequent nursery, you will probably be able to decrease the pauses, of the local collects. But if there is a survival rate is relatively high, then non-generational workload, sorry, the generational GCs are probably losing its benefit. So if your workload has, for example, uh, characteristics of a session, so you create a session, it lasts for several seconds or sometimes minutes, and then you tear down a session. That means that there are objects that are going to live around for several seconds, several minutes, and that means it has non-generational characteristics, so those things are a relatively good candidate for reducing or maintaining a relatively low gap relative to generational collector like a Genco.
The distribution of object sizes, is that predetermined per each application, or how is that determined?
That's static. That's static. Actually, that's one part that you cannot control. It starts with 16 bytes, and roughly each class size is, I believe, I forgot, 25% larger than the previous one, up to 2 kilobytes. So something like 100 bytes is size class and 125 bytes. Although they're certainly 8 bytes aligned, but they're 25% apart.
Have you ever considered using a buddy system like a binary buddy or Fibonacci buddy system to deal with that? You get the same, I think, the same goal, controlling fragmentation. You get about 25% internal fragmentation typically with binary buddy. Have you ever considered that?
Yeah, certainly those variants are possible, yes.
Are there any other questions? All right.